This video is about the Thevenin equivalent of a voltage divider. It corresponds to section 5.1.2 of the Applied Analog Electronics textbook. And incidentally, I'm almost certainly mispronouncing the name Thevenin. I'm using the standard American pronunciation, but I believe it's actually a French name. It's got an accent. And if you wish to use the French pronunciation and know what it is, feel free. You'll hear most American engineers using the American pronunciation. Okay, what Thevenin's theorem says is that if you take any circuit that has only two ports, that is only two connections to the outside world, and consists of just resistors, voltage sources, and current sources, then you can represent it as a resistor in series with a voltage source. And this resistance is known as the Thevenin resistance. This voltage is known as the Thevenin voltage. In particular, from our standpoint, there is a circuit that we use a lot where we've got a voltage source, I'll call it Vn, and we have a voltage divider, and we have our two ports being the output of the voltage divider. That circuit is our standard voltage divider circuit. It has a Thevenin equivalent. So let's give some names to these two resistors. We were using Ru and Rd before, so let's stick with those. What we want to do today is to figure out what is the Thevenin equivalent of this voltage divider circuit. Okay, what we're going to do is to look at what currents we have. And there are three currents we can look at. I will call this one IU, the one that goes through the Ru resistor. I'll have one called ID, which is the current that goes through the Rd resistor, and I'll have another one let's just call this A and this B, so this is IAB. The current from port A to port B in whatever external things we have connected to this. And what we want to know is, what is the relationship between IAB, and the rest of this? Because we can determine how this thing behaves if we can find an equivalent circuit to this one that gets the same behavior for voltage and current at these two output ports. Because the whole idea of the Thevenin equivalence is we can't see what's going on inside the box. This is a closed box. We can't see what's in it. All we can do is put voltage across it, measure current. And so if we can get the same voltage current behavior from this circuit as from this one, we've gotten the equivalence. All right, so how are we going to do that? Well, basically, we're going to use Ohm's law and try to figure out what is going on here. We have got that the current through Rd is just going to be VAB, the voltage of the two ports, divided by Rd. We can look at the IU. Well, that's going to be the voltage across that resistor, so that's Vn minus VAB divided by Ru. And finally we have IAB, which we really don't know much about. It's our external current. We don't know what's going to control it, but we do know one thing, and that is that the current through this resistor is going to be split and flow through these two things. So IAB plus ID has got to equal IU. There's no other place for this current to go. This is Kirchhoff's current law, that current doesn't, you don't have charge accumulating in one spot. current coming in has got to go back out again. Okay, so we've got three equations here. What can we do with them? Well, we can do some substitutions in here and sort of put all three together to get rid of the ID and IU ones there and get IAB plus ID is VAB over RD equals VN minus VAB divided by RU. So that's an equation that gives me the relationships between IAB and VAB with some constants in here, the RU, RD, and VN constants. But it's not in a very nice form. So let's try rearranging that a little bit. See if I can get that still on my screen. All right, so first thing we want to do is we've got VAB on both sides of the equations. And that's not Vn times VAB, that's Vn minus VAB. Sloppy writing there. Okay, so we want to get VAB on the same side, and let's get all the VABs together and everything else on the other side. So we would have VAB times 1 over RD plus 1 over RU is equal to, what do I have left? VN over RU minus IAB. Okay. I can simplify this even further by saying that VAB, the output voltage, or the voltage between the two output ports, is Vin, and I'm multiplying by this, so that's going to give me, let's see, what would that be? R comes out to RD over RU plus RD. And then minus IAB times, and then I would just have 1 over RD plus 1 over RU. Okay, so what does this tell me? I've got something here that says this is a voltage, and it's a constant voltage here. Notice all these things don't involve current at all, minus the current times a constant resistance. Well, if we take a look at what that is, if we put V threshold and we have A and B here, what are we going to have across AB? Well, how much current do we have? If we've got current flowing, now that from A to B, that's current flowing this way, external current from A to B, then we're going to have, as the current increases, we'll have a voltage drop across here. So we're going to have V threshold minus IAB times R threshold is VAB. That's in the same form as we have up here. What we have is that the V Thevenin is Vn times RD over RU plus RD, and R Thevenin is 1 over RD plus 1 over RU. Okay, what does that mean? That means that we can think of the voltage divider, if we're looking at just the output of the voltage divider, and there, going back to the original circuit, the output of the voltage divider is across this lower resistor here. If we think of that, we can just replace the entire voltage divider circuit here by a voltage source whose voltage is exactly what we previously computed the voltage divider voltage to be. If we take no current from our voltage divider then we get the voltage divider current, so Vn times Rd over Ru plus Rd. If we take current from it, we're going to reduce the voltage we get across there, and the equivalent resistance, so if we have that voltage source and then put a resistor in series with it, the equivalent resistor would be what we would get from putting Ru and Rd, these two resistors, in parallel, because this is the same formula we had for parallel resistance. So Thevenin equivalent of a voltage divider has a voltage source that's the voltage divider voltage, and has a resistance that is the two resistors of the voltage divider in parallel. And that's a very simple formula to remember, because you already needed to have memorized both these formulas for other purposes. Quite often we will use Thevenin equivalence to simplify the analysis of a circuit, because this equivalence is something that we can do whenever we have any sub-circuit that is part of a bigger circuit. We can take that sub-circuit and replace it by its Thevenin equivalent, and then have a simpler circuit to analyze when we include the stuff around it. Okay, that's probably enough on Thevenin equivalence for now. We'll have some exercises on it and some quiz questions and things like that, and you'll be using it in various ways in the future.